Okay, so hopefully we are now able to find the response of the system to any input, because now that we have the impulse response, we just perform the so-called convolution. If you have the x of n, the input, and if you have the impulse response h of n, just convolve x of n with h of n, and we know how to do that. One by one, you measure the output for every impulse in your input, and then combine the responses at the output. That is one way to do it. Fortunately, life is a little bit easier than that, because there is the concept of graphical convolution. Graphical convolution is the same convolution. What was convolution? Let me write it again. X of n was equal to y of n. The output was equal to, for a variable from minus infinity to plus infinity, m x of n delta n minus, it's not delta anymore, sorry, h n minus m. So this was the convolution of x and h, the formula of convolution. Now this formula, providing the same thing, has an alternative way of computation, okay? And that is the graphical way of computing the convolution outcome. The graphical way is a little bit easier for many students, and for me as well, is a little bit easier than individually, one by one, finding the impulse responses and then accumulating or finding the summation of the responses, as we did. It's as follows. Let's now have a separate axis of m for two signals. Okay. On the axis of m, we will have an accumulation, because it's a summation of it's a summation over m from minus infinity to infinity. So we will accumulate over this m axis. But what's going on this axis is the question here. The first one, this first signal is x of m signal. Let's draw an example, x of m. This is nothing but one example, x of m. At m is equal to minus 1, it is x of minus 1, and x of minus 1 is, let's say, 1. X of 0 is 2, x of 1 is 3 on the axis of m. So if you draw it on the axis of n, it will be exactly the same. It will be that time x of n. Okay, but this is, I'm just giving the axis name of m. If I draw it on m, how do you, or how can you draw h of n minus m on the axis of m, not on the axis of n? On the axis of n, we know that h of n minus m is the same as h of n shifted by an amount of m to the right. If m is negative, then it will be shifted to the left. But on the axis of m, how does it look like? First of all, on the axis of m, h of n minus m is h of minus m. We have to give some landmarks, some specific points for n. Let's assume n is equal to 0. When I say n is equal to 0, the summation here will give me y of 0. Because, well, n is equal to 0 here. So if I multiply xm by h of minus m, 0 minus m, and add them up for all m, I will get y of 0, n was 0. So for n is equal to 0, for example, what is h of minus m? How do we draw h of minus m? What's the way to draw it? We just invert it in time, okay? Time flip around. Instead of h of m, now we have h of minus m. Let me open a small parenthesis here, saying that h of n on the axis of n was, let's assume like this: 1, 1, 1. Okay, like this. It's a large parenthesis, and I'm closing it. So h of n was like this. So what can you say about when n is equal to 0? How does so this is x of m. How does h of minus m look like? It must be flipped towards the negative side, which will give you 1 here, 1 here, and 1 here. At oh, sorry, the axis is a little bit incorrect. This is the 0 axis, right? So 1, 1, and 1. At 0, minus 1, minus 2, and all the others are 0. So this is h of minus m. h of minus m corresponds to n is equal to 0. When n changes, let's assume when n is equal to 1, what does h of 1 minus m look like? This is h of 0 minus m. What does h of 1 minus m look like? It is shifted. And it is shifted towards right. So h of 1 minus m, when n is equal to 1, will be the same shape, shifted towards right. So it will start from minus 1. It will go on 0, and it will go on at 1 again. 1, 1, 1. But shifted towards right. If n is something larger, it will be even pushed further towards right. If n is negative, for example, if n is equal to minus 1, what does h of minus 1 minus m look like? It will be shifted towards left this time. If it is minus 2, it will be shifted towards left once more. And it will go to the left hand side. So by changing n, the original time variable of our output, I'm just shifting the flipped around version of h. First I flip it around and I shift it to the right or to the left by changing n. For n is equal to 0, I hope you have taken note of this h of n, because I'm gonna erase it, because I'm gonna need the bottom part of this graph. Okay, so I'm erasing it now. It's just the way that I'm representing h. Now look at the formula. When n is equal to 0, we have to multiply xm and h of 0 minus m, these two shapes. They must be multiplied, right? And they must be accumulated, summed up for all m. So let's multiply them. So I'm going to draw x of m times h of minus m, the multiplication. What is the multiplication? Sample by sample we need to do this, but most of them are just zeros. And at minus 2, this signal at the top is 0. At minus 2, this one is 1, so their multiplication is still 0. Isn't it? And then at minus 1, so at minus 2 it's 0. At minus 1, the value here at the top is 1. The value here is 1. Their multiplication is 1. At minus 1. At 0, this has a value of 2. This has a value of 1. And their multiplication is 2. At 0. At 1, this is a value of 3. The other one is a value of 0. So it's 0, and all the others are already zeros. So to the right and to the left, this multiplication of these two signals, sample by sample multiplication, will give you this combined result. But that result doesn't correspond to anything unless you accumulate these values. What's the accumulated value? What's the summation of all these values from minus infinity to infinity? It's 0 plus 0 plus 0 plus, etc. Plus 1 here and plus 2 here. So what is summation xm h minus m for all m? It's equal to 3. It gives you the result at which point? At n is equal to 0. So I say y0 is equal to 3. I evaluate the output at a particular point, at a particular time index. That is 0 index only. Now let's go back. xm and hm here. How can we evaluate, let's say, y1? We have to say n is equal to 1. So we don't need to have h of minus m, but we need to have h of 1 minus m. Do you remember what h1 minus m was? It was one shifted to the right version of this flipped around thing. So it's not h of m anymore, it is h of minus m anymore, it is h of 1 minus m. Let's shift it towards right. Okay, I'm gonna enjoy what I'm doing, but I don't know how you will take notes of these things. Because I'm gonna erase everything here. And I'm gonna erase this. I will say n is equal to 1. And I'm gonna erase this. And I will put a 1 here. So that would make h of 1 minus m now. What I did is quite simply shifting the previous shape towards right by 1. And then we need to do the same thing. We have to multiply them. Let's multiply. The multiplication is x of m times h of 1 minus m. And the multiplication is at minus 1, 1 times 1 is 1. At 0, 2 times 1 is 2. And at 1, 3 times 1 is 3. Sorry, let's make it somewhere in between. Like this. Assume this is 2 and this is 3. At minus 1, 0 and 1. And then of course I have to accumulate this time x of m, h of 1 minus m. I must sum them up for everything. What is the summation of 1, 2 and 3? 6. So what is this 6? Y of what? 1, right? N is equal to 1. This is equal to 6. And then you may guess that I will cheat again. This time I will say n is equal to 2. And I will take a look at h of 2 minus m. And h of 2 minus m will be, well, here. Shifted again towards right. And what will be the multiplication? It will be x of m, h of 2 minus m. And the result will give us the value of y at n is equal to 2. We will find y2. So when I slide it towards right, what is their multiplication? This is 1 times 0 here, so it's 0. This is 2 times 1, that is 2 at 0. This is 3 times 1, that's a 3 at 1. And this is 0 times 1, so all the others are 0. And I have to sum up now all these things to find x of m, h of 2 minus m summation, and that summation is 5. So what did we find? We found y of 2 is equal to 5. And again, at n is equal to 3, I'm going to erase this, and I'm going to put a 1 here and make it a 0. Shift again towards right. So this will be h of 3 minus m. And the multiplication will only give me one sample at 1, which is 3. The others will be all zeros. You see that? The multiplications will give you zeros. So there is only one sample left, and that is y of 3. And what's the summation of that thing accumulation? 3, only one sample. What would you say about y of 4? 0. Because if I slide this top h of n minus m shape further towards right, it doesn't overlap. There is no overlapping now. So I can slide only some finite amount as long as they overlap. But that's not the only thing, unfortunately, because, okay, y4 is equal to 0, y5, and all those things are all zeros. It will go on like this. But how about y minus 1? We just didn't evaluate that one, unfortunately. Let's also have minus 1. The original was like this. Just to make a reminding, h of minus m was this. So what is h of minus 1 minus m? It further shift towards left. So it's this. Just once at minus 3, minus 2, minus 1. Okay? And unfortunately, as you see, there is an overlap with the top x of m shape. When you multiply, cross multiply these things, it will give you h of minus 1 minus m to be equal to 1 here, and all the others are 0. So I have to put an extra term here. Y of minus 1 is equal to, what's the summation of all these things? There's only one term, which is 1. So y of minus 1 is 1, y of 0 is 3, y of 1 is 6, y of 2 is 5, y of 3 is 3, and all larger y of n's, starting from 4, are 0. If you further push this thing towards left, it doesn't overlap. It starts not overlapping again. So y of minus 2 is also 0, because they don't overlap, no multiplication. So y of minus 2 is 0, y of minus 3 is 0, etc. It goes on like that. And when you draw this thing, what does it look like? At 0, it's 3. At minus 1, it's, sorry. At minus 1, it is 1. So 1, 3, then 6 at 1, then 5 at 2, and again 3 at 3, and the others are zeros. And this is y of n that I have drawn on the axis of n. So I evaluated it like this. What did I do now? I said graphical convolution, so there must be a graphical way of convolving things or computing the convolution. The thing that I did is I flipped around h and then slided it towards left and towards right. The amount of sliding determines the point that I evaluate. If I don't slide, if I keep it there, it corresponds to n is equal to 0. If I slide it towards right, it would correspond to n is equal to 1, 2, 3, etc. Goes on like this. If it goes towards left, it will be minus 1, minus 2, minus 3. Flipping around and sliding h, but while keeping x shape. There are very nice Java applets on the web, and I used to have one before my web page under the engineering faculty domain was demolished. Okay. We don't have any domains under our control now, so I'm unable to put my Java applets, unfortunately. I'll try some ways. At least I'll try to install it into this computer and illustrate it here, at least, let's say, tomorrow or next week or something like that, if I can run them in a local computer. But it was on the web pages. But nevertheless, you can still find very nice open courseware applets for convolving signals. Discrete time convolution. Okay, so these are the code words, the keywords. Discrete time convolution Java applets. Okay, just write these on Google, and then you will probably be able to find some nice Java applets. What are those Java applets? On those Java applets, you just draw with your mouse some input x of n, and then you draw h of n, an impulse response. And the applet immediately flips around that h of n and starts sliding it so that you can see how many of those things will overlap, which will produce what value at the output, one by one. That is the way that you are supposed to perform convolution, discrete time convolution, flipping around, sliding, and evaluating. After multiplication, you accumulate, that will be the evaluation. Since most of the time these two shapes are finite, you will have to slide only a finite amount. As long as they overlap, you have to evaluate. But you shouldn't go to non-overlapping regions, of course. They will all be zero. That would be a useless way of insisting on the convolution. So this is the graphical way of performing convolution. You flip around H. Very soon we will, well, I can say it right now, this convolution has a symbol, and that is a very linear operator, okay? The operation, the concept of convolution is something quite linear. This is the notation. We will say that y of n is the convolution of x and h. Look at the star in between. That star is the convolution operator. It's like summation. It's like multiplication. But it's not. It's convolution. This star will correspond to that. And if you take a look at the notation in the book by Oppenheim, you will also notice the same. In fact, in all the books, they use convolution as a star operator. And the way to evaluate the convolution is flipping around H, sliding, multiplying, and accumulating. The amount of slide will give you the index of n, y of n. Now I need to make sure that this flipping around, sliding graphical way is equivalent to what I have told you the previous hour. So this is the notation. Okay, let's keep it in mind. But I will solve the same question here in an alternative way. It's not the alternative way, it's the real way. The graphical way is the alternative way, of course. The real way was like this. Again, let's remember our signal, x of n. Now on the n axis, this time not m axis, it is 1, 2, and 3, isn't it? At minus 1, 0, 1. And we have h of n, which is the impulse response of this linear and time invariant system, to be equal to 1, 1, 1. All the other values are zeros. Okay? What was the original way to evaluate this? It was this. We split our x of n into impulses. Obviously, there are 3 impulses in this x of n. The first one, let's start from the leftmost. What's the leftmost impulse? It is at minus 1, and the magnitude is 1. So what is the response to this? I will put a 1 here. So the first impulse response will be, let's say, h1 of n. It is just shifted towards left, and the scale is 1, so there's no scaling. And the response will be therefore just shifted to the left of the impulse response. This one. Is that okay? Okay. Now, what is the second impulse? It is here, the central one. And the scale is 2. but there is no shifting in time. So we don't go to the left or to the right. Let's call it 2. The 2 will produce at the same position of h of n, but scaled by 2. Right? So it is 2, 2, and 2 at 0, 1, 2. Let's call it h2 of n. Okay? The response to the central impulse. And then there is one more impulse. It's this one. Let's call it the third impulse. Where is it? It is shifted towards right by 1, and it is scaled by 3. So we have to scale this h of n by 3 and shift it towards right by 1. And the shape will be, we can give a name to that shape if you wish. It is h3 of n. That is equal to 3, 3, and 3. And they are all shifted towards right by 1. So this one is 1, 2, and 3. The others are all zeros again on the axis of n. So these 3 individual impulses produce these individual responses. Impulse versus impulse response. And what are we going to do? Since the input is the combination of all these 3 impulses, the output is the combination of all these 3 impulse responses. So we are going to add them up. And the summation will be y of n. Again, unfortunately, the window size is a little bit small. So we have to start from -1 because all the others are zeros, but at -1 there is a 1 term here. So 1 plus 0 plus 0 will give you 1 at -1. And then we have 1 here at the top, 2 here, and a 0. So 1 plus 2 is 3. 3 at 0. Then at 1, this is 1. This is 2. This is 3. What's the summation? 6. At 1. At 2, it is 0 plus 2 plus 3. It's 5. At 2. And at 3, there's only 1 term, the others are 0, so it is 3 plus 0 plus 0. It's a 3. After 4, of course, there's nothing. Just like before -1 there was nothing, and after 4 there is nothing. Look at this y of n. Fortunately, I'm very glad because I'm just on the spot trying to solve this question. I'm happy to see that, as far as I remember, this is the same y of n as this one. 1, 3, 6, 5, 3. So they are really 2 alternative ways of looking at things. You can choose either way. Whichever you remember better, whichever makes more sense, or whichever is more easier for you to compute, just go ahead and give us the convolution result, which will give you the output of your system, which is y of n here, and y of n here, as you see. So that's the way you do it. There is an example now that I would like to make. Which I find a little bit difficult in one way, which is the last way that I did, the impulse response combination way. But if you slide, it will be a little bit easier. Look at the example here. I'm giving you x of n. Of course, I have to give you 2 things. I have to give you the input and I have to give you the impulse response, x and h. And all you need to do is to convolve them to find the output. X of n is not very graphical this time. It is alpha to the power n u of n, where alpha is less than 1 and greater than 0. It's a positive, let's say, small number, so that this series converges. Okay. U of n forces this series to start from 0, and it goes to the right hand side, because U of n is all ones for positive n, and it is 0 before 0. If you try to plot this, just as an illustration, how would you plot that? It is something like, you don't need to do it that way, and I don't need to do it that way, but I will do it anyway, just for making sure that we understand everything. This x of n really looks like this. There is a 1 at n is equal to 0, because alpha to the 0 is 1. And then, what? And then alpha to the 1, that's alpha. And then alpha square. And then alpha cube. And then alpha to the 4, etc. And it's a decaying exponential. Okay, it's a decaying exponential, starting from 1 with a rate of alpha. That's what this input is all about. And so it's an infinite sequence. The input is infinitely long. We may have a problem here, right? Because in the previous cases, I just gave you examples of some finite sequence. We have 2, 3, 4, 5, some finite number of impulses. But now, the input, if you try to decompose into impulses, you will need infinitely many impulses. So that's why this example is critical and a little bit different from the previous ones. Besides, look at the impulse response. H of n is equal to U of n. So the impulse response is also infinite extent. It starts at the position of the impulse, but then it stays. It's like a capacitor sort of thing. Okay? This is the impulse response. And it is, again, infinite extent. Let's try to draw it. It's easier to draw this one. All ones. And all zeros before 0. Like this. So these two are the things that we have. Now you have to be a little bit smart in order to give an analytical expression, a mathematical expression to the response of your system to this input, to the input which is exponentially decaying. And what are we going to do? I would choose flipping around and sliding. Okay. Let's flip around this h of n, because that's what we flip around, right? We flip around h over the 0 axis. So this is now what's that? On the axis of m, let's flip around this. This is what we get. So this is h of minus m on the axis of m. Okay, I flipped around the top figure. Where does this correspond to? Without any shifting or anything, it corresponds to n is equal to 0. So at n is equal to 0, this is the situation, and we need to multiply this bottom shape with this top shape. When you multiply, you see that merely only one sample is multiplied. So if you go any further towards left, there will be no overlap. So the output from here, I can say that the output is all zeros for negative n. When n is equal to minus 1, there's no overlap. This will go to the left, and it will not overlap with the top figure. So the multiplication will be 0. For minus 2, minus 3, for all negative numbers, it's a 0. But at n is equal to 0, there is an overlap. What is this? It's the multiplication of this and this. What's the value of that? 1. So the multiplication is one impulse in the center. And when we add all the others with all the other zeros, I will say that y of 0, y of n at n is equal to 0 is equal to 1. Yeah. Now let's take a look at 1 minus m. What's that? It's 1 shifted towards right. Here, an extra term enters. Okay? I shifted it to the right. So it will give me y of 1. And we need to multiply this shape at the bottom with this top shape and then add the multiplication or accumulate the multiplication. What are those multiplications? There is 1 times 1, which is 1, and then there is alpha times 1, which is alpha. So it is 1 plus alpha. Good. Y of 1. 1 plus alpha. Now, let's take a look at h of 2 minus m, which is one more shifted towards right. Now there are 3 terms that are added. 1 times 1 plus alpha times 1 plus alpha squared times 1. So the answer is y of 2 is equal to 1 plus alpha squared. And you already get the picture, right? Every time you get you insert a separate one more impulse here, they will be multiplying alpha cube, alpha to the 4, alpha to the 5 by 1, and it must be inside your accumulation. So you can see that y of 3 is equal to 1 plus alpha squared plus alpha cube. And in general, y of n is equal to what? Yes, let's write it in a summation form now. We need a more compact way of writing things. That is equal to k from 0 up to n, okay, alpha to the power k. That's it. This is one of the most compact ways of writing things, but it is not the most compact way of writing it. It's a series summation. You may remember it from calculus. What is it? What is this summation? It's a power series sum, but it's not an infinite power series sum. 1 minus alpha to the power n, no, the limit is n, plus 1 divided by 1 minus alpha. So this is the formula. For a general y of n, for n greater than or equal to 0, of course, the summation doesn't work for negative n's. So the student who is able to give me this answer or the other answer that I will write, if you give me this answer, you will get 10 points out of 10 points. It's equal to 1 minus alpha to the n plus 1 over 1 minus alpha when n is greater than or equal to 0, and 0 else. If you write it like this, you'll get 10 points. You will also get 10 points, plus maybe I can give you some bonus from some other mistakes. I can eliminate some of your mistakes. You may get 11 or 12 points if you give the answer like this. I really enjoy such an answer. 1 minus alpha to the n plus 1 divided by 1 minus alpha times u of n. If you write it like this, you automatically make all the negative n's to be equal to 0, and you make this formula to be valid only for positive n's. Brilliant. Okay? So this is the best answer. for this question. And for small n and for larger n, how does it behave? Let's try to analyze this output. Let's try to visualize this output. The output is starting from 1, first of all. When n is equal to 0, so y of 0, it is 1 minus alpha over 1 minus alpha, which is 1. The output is 1. And then it becomes 1 plus alpha, and then 1 plus alpha square. But since alpha is less than 1 in magnitude, alpha to the power n will be smaller and smaller. And as n goes to infinity, what does this value take here? What's the value that we get? Say it. What is the infinite summation, in other words? Not up to n, but when n goes to infinity, it is 1 over 1 minus alpha. Because alpha to the infinity will be 0. Alpha is smaller than 1 in magnitude, so alpha to the infinity will be 0. 1 minus 0 over 1 minus alpha. 1 over 1 minus alpha, in other words. That is the ultimate value. 1 is the starting point, and somewhere here, I don't know, 1 over 1 minus alpha is the ultimate value, and it is asymptotically increasing to this limit value as it goes to infinity, starting from 1, 1 plus alpha, 1 plus alpha square, 1 plus alpha square plus alpha cube, plus etc. It goes on like this. So this is the output graphically, trying to converge to 1 over 1 minus alpha. Suppose alpha is equal to 0.5, less than 1, obviously. If alpha is 0.5, what is 1 over 1 minus alpha? It is 1 over 0.5, that is 2. So starting from 1 and increasing up to 2, it will make. If alpha is equal to 0.8, what will it be? From 1 climbing to 5. 1 minus 0.8 is 0.2. 1 over 0.2 is 5. Yeah, so something like that. Now, okay, we are running out of time. I want you to repeat this, at least graphically, and make sure that one by one, the term really corresponds to that. And it's the more difficult part, but you have to be exercising, as I said in the beginning. Please do the same example by impulse response accumulation. So this h of n is the impulse response. You have several impulses, shift them, scale them, and sum them up, and see if it really corresponds to this strange formula. That's a critical exercise. Please do that. I may ask it in the examination.